Alright, so now we will solve how to calculate the boiling temperature of water at 8,000 meter of altitude. So this is important. So if you see, you need to keep in mind this information. 8,000 meter of altitude, right? So in this case, we already know the boiling temperature. So I explained this concept, and if you see my last tutorials, then what I said is water is start boiling at 100 degrees centigrade temperature, isn't it? Yes, and at atmospheric pressure. So in this case, the question is, we need to calculate the temperature, the boiling temperature of water at 8,000 meter of altitude. So the important thing is we need to calculate the temperature, that's it. And the only information given here is the altitude, which is 8,000 meter. Now what I said, if you can remember, water start boiling at atmospheric pressure. So if we calculate, if we know the atmospheric pressure at 8,000 meter of altitude, then we will try to find out the corresponding pressure for that atmospheric pressure. So let's have a look at this table. If you see here at 8,000 meter altitude, the atmospheric pressure is 3.565 into 10 to the power 4. So it's in Newton per meter square, that's the unit. So keep in mind, this is 3.565 and this is the 8,000 meter altitude. We got the atmospheric pressure is this. If you can remember the boiling temperature, what I said last time, and maybe you will get something in my first video of this tutorial, that means the Tut-1 part 1. So water start boiling at 100 degrees centigrade temperature, that means the vaporization state, and the water vapor try to escape but they can't, and they create some pressure on the water surface. We say this is the vapor pressure. So actually this atmospheric pressure is the vapor pressure. And now let me solve this problem. I'll definitely explain. Just let's start with this. Okay, so see what I wrote here. At 8,000 meter of altitude, the atmospheric pressure is 35.7 kPa, or this value we got from the table I showed you earlier. This is the atmospheric pressure. And now if we go back to the table, you see the actually the water properties. See this atmospheric pressure, the water vapor will create the pressure at the the water interface, the water surface. This is called the vapor pressure. So we can see from this water properties, the physical properties of water, you can see this is the vapor pressure. So what I found here, see the vapor pressure is increasing with the temperature. At 100 degree temperature it is like this, but what we got at 8,000 meter altitude, the atmospheric pressure is 3.5 something, and it is here. You see this is 3.11 and this is 4.734. So that means the atmospheric pressure at 8,000 meter altitude sits in between these two values. That means the corresponding temperature will be in between 70 and 80. That means we need to use these two values, and then we need to do some interpolations to get the temperature. So what I did here is I said we need to find out the corresponding temperature. So the vapor pressure of water at 70 degree and 80 degrees centigrade used for this interpolation. At 70 degrees centigrade, you see this is 3.11, and 80 degrees centigrade it is 4.734, and this is the atmospheric pressure, that's the vapor pressure, and we need to calculate the temperature for this pressure. This is actually the question. So now when we don't know the values, exact values, then what we do usually, we do some interpolations. So now we will do some interpolation. I already have one video on my channel, so you will see how to do the interpolations. But the simple thing is, when you will do the interpolation, so say this is the left hand side. It's somehow I wrote it here, but it should be here, but it doesn't matter. So what you need to do is, what you are looking for, t, okay, write down t minus the initial value, what it is, 70, t minus 70 over the end value minus the initial value. You see 80 minus 70. So this side it will be the same thing. At first the middle one, 3.565 minus the initial value, and then the end value and the initial value. Now you can ask me, okay, we had the value 3.565 into 10 to the power 4, why you didn't write this 10 to the power 4? So it is 10 to the power 4 is with all of these values. To just make it simple, I just did not write it down here, so it's okay. So you can do the same thing. So now you see we already got these equations, these relations between this left and right hand side. So now we need to simplify this. That's it. You see all are the constant values except this is the unknown variable. So if we simplify, then we'll get the temperature T. So it will be 72.8. Okay, so this temperature is 72.8 degrees centigrade. That's it. So this is actually the value we got. So this is the the boiling temperature at 8,000 meter of altitude. So I believe you got it, why I use 70 and 80 degrees centigrade temperature. So now the next question we'll solve is, alright, so the next question is we need to solve the sound speed. We need to calculate the sound speed in the air, and the first one is the sea level. Okay, so at sea level and in a standard conditions, so an 8,500 meter altitude, and the other one is you see here the sound speed in sea water at 15 degrees centigrade. So the air at sea level at a standard condition. So like I said, if we solve this, it is something like this. So this is actually the formula to calculate the airspeed, or the air sound, or air, this is called airspeed. So it is k equal k, a equal k, r, t, and square root. If we consider air is an ideal gas, then this is the relation. So if you ask me how you got this equation, I will tell you this is something you will get it in your book, or you can see some physics chemistry books, then you will get there. So but I think it is in your book. You just look it, and then you will get all the equations actually how to drive this. But the basic thing here is you need to know what is K, and what is R, and T is the temperature we all know. So K, this is the heat capacity ratio. This is constant. If you see this definition here, K equals Cp and Cv, you will get these relations from any chemistry books. You will see what is the relations between Cp and Cv. So this is always constant 1.4, so you don't need to worry about this value. R, it is actually the gas constant. So the gas constant value is 287 joule per kg Kelvin. So this is also constant value, so you don't need to worry about these two values K and R. But you should think about the temperature. When it is the sea level air, then the standard condition, the temperature is 15 degrees centigrade. Okay, so when it is the air at sea level, the standard temperature is 15 degrees centigrade. You will find one of the table. If you see the slide, I have included some information, standard sea level conditions, and the corresponding pressure, density, temperature. You see everything is here. This is 15 degrees centigrade. So you will get the detailed informations from the slide that I shared in the file exchange section of your Tut group. So it's pretty simple. If you substitute all of these values and simplify, this is the square root, you will get it is 340 meter per second. That's the the sound speed at sea level in standard conditions. So now the second part of this question is, what will be the value at 8,500 meter altitude? Right, so at 8,500 meter altitude, the only thing you need to consider is what is the temperature at 500 meter altitude. So you got the table. I showed you every informations in the slide that I uploaded. So at 8,500 meter altitude, temperature is 40.2. So convert it into Kelvin. The capacity ratio, gas constant are always the same. Only the variation is the temperature. So if you put it here, then you will get the value. So 355. That's it. And the next question is the sound speed in seawater at 15 degrees centigrade. So at seawater, the equation will be a little different. You see it is A over rho and this half. That means this is the square root. E is actually the bulk modulus of elasticity. A is the sound speed and rho is the density. So the bulk modulus of elasticity for seawater, this is 2.34 10 to the power 9. You can ask me how you got this value. This is constant. I have included all informations. You see, this is the bulk modulus of elasticity for different fluids like water, seawater. So now we are solving the questions for seawater. In the quiz, you might get some questions for maybe water or maybe any other fluid. So you need to know this value E. So if you know this value and at standard conditions, that means it says the seawater and 15 degrees centigrade. So at 15 degrees centigrade, it is 1030. You will get, I'm telling again, you will get every single information here from here. This is for the standard sea level conditions. So, and now if you substitute all value here, so this is the sound speed in seawater. So that's pretty simple, and now we'll solve the next problem. Alright, so the next question is the maximum diameter of 5 centimeter long circular cylinder. So this is a 5 centimeter long circular cylinder, cylindrical steel needle. Density is given 8,000 meter. That can float on the water surface at 20 degrees centigrade. Okay, so at 20 degrees centigrade. What actually you need to calculate here? Is it the diameter? No. So the diameter is given, the maximum diameter of a 5 centimeter. Now you need to calculate the diameter, the maximum diameter, and this is the length of the cylindrical steel tube. So this is important section here. You see the maximum diameter. That means if, let's say, this is the needle, or maybe something like this. Maybe is something like this. It says maximum diameter. That means the diameter throughout the needle, it is not uniform. So it is non-uniform diameter. Okay, so we need to calculate the maximum diameter. That's it. The only information given is the length, the surface, temperature, and the density. So now we need to know actually when an object cannot float on the water surface. You can remember I explained the surface tension earlier. So the surface tension is the main mechanism here that actually help to float an object on the water surface. So for any falling objects which is falling, it can float if the surface tension is equal to the weight of the objects. You know what I mean? The surface tension of the object, if it is equal to the weight of the object, then only it can float. So the surface tension of this, the steel, cylindrical steel needle is this, and this is the weight. So sigma, this is the surface tension coefficient, and this is the constant value 0.0728 for steel needle. So you will get it from the table. So if you search it, you will get this value sigma. If you look here, this left hand side equal to this, so we can easily eliminate this term L, so it just cancel out. That means, okay, then I will say this on later, and if we simplify, then sigma, it will be pi d square rho g and 8. So we need to calculate the maximum diameter d. So if we write d square equal, it should be 8 sigma and pi rho g. Okay, so this is actually the relation we got. D square, it is equal this. Okay, so we know sigma, we know the pi is constant, we know gravity, it is constant, and we know the density is 8,000 meters. So if we substitute the value here, then we will get the solution. Alright, so what I said is, now we will substitute all value, and you see we got it is 1.56 millimeter. But now I actually want to tell you something. Suppose this density, it is given here, but if it is not given, you see, you can simply use this density equal 8,000. But if it is not given, you will get some question in the exam, and the density is not given, then how you will calculate it? Simply, you will jump to the table. You will see, okay, what is the in the materials? It is water. So the water density is 998 or 1000. But this is not correct because surface tension is acting here, and this is the cylindrical needle. The steel needle, it has some sort of a specific gravity. So on the water surface, if the density is not given, so the density, it will be equal to the water density and multiply the specific gravity of the materials, which is the steel needle here. So I'm telling again, if this density is not given, and if you use the density rho equal 1000 on 998, then it should be incorrect. It's not correct. You need to calculate the you need to know the specific gravity, and then you will multiply the specific gravity with the water density, and then you will get the density here. So that's the key thing you need to keep in mind when you will solve this sort of problem. Now, come to the point. It says, what will be the, and similarly for 10 centimeter long needle, what should be the maximum diameter? You see, we already cancel out this length, right? That means length is not important here. It doesn't affect the solutions. So which means it doesn't matter if you consider a 50 centimeter long steel needle, still the maximum diameter should be this. It will not change your solution, so the maximum diameter should be same. Alright, so this is the last question today. Now we will solve this question. You see, it says in the arrangement shown, determine the speed, that means you see the velocity with which the circular cylinder would fall when the steady state has been reached. The cylinder is made of steel with this density, and the wire has the viscosity. So we need to calculate the speed of the circular cylinder which is falling, and we need to calculate the speed when it reaches the steady state condition. That means the velocity is not changing with time, and that means it is quite stable. This is the frame. You see this solid object. This is actually the falling, the cylinder, steel cylinder, and its diameter is given on 49.8. On the other side, the diameter of this frame, it is 150 millimeter. So you see this is 150 millimeter from here to here, and 149.8 from here to here. So that means we have 0.2 millimeter wire film. So this is the wire film and it is falling this way. So gravity is acting this way and the length of this cylinder is 200 millimeter. The other information we know is the density of the material, the steel, and the wire viscosity. That's it. So we need to calculate the velocity. So now a couple of things working here. Actually, I would like to explain this problem little different ways. So what I said is we need the velocity. So the couple of things happening here. Our ultimate target is we actually need the velocity v, and shear stress is one of the key thing happening here because this object is falling this way. So if I just don't spend a lot of time with this, so let's say just quickly solve this question. We need to calculate the velocity, and we know shear stress is function of velocity. You see here, this is tau, the Greek symbol tau. We can define the shear stress is tau equal mu, the dynamic viscosity, and the dv over dr. This is the velocity, the change of velocity, and this is the change of the diameter. R is the diameter, v is the velocity. So if you look at this relation, so if we know the shear stress, if we know the mu, the dynamic viscosity, and the r diameter, then we will get the velocity. So look at this from these relations. We already know this viscosity, dynamic viscosity of water oil. This is constant value. The diameter r, you see this is given for this problem, the cylinder and this frame. The diameter is given, so that means this r, this is also known, and this b, this is our ultimate target. So 2 known and 2 unknown, and this is the final target. If we can calculate the shear stress from other definition, then we will get the velocity. So our first target is we will calculate the shear stress. Okay, so let's see. There is the other definitions. Shear stress is the weight over area. So in other words, if we divide the weight by the area, then we will get the shear stress. So that means we can easily calculate the area when we know the dimensions, length, the diameter. Then we can easily calculate the area. But what we need to know is the weight. So that means to get this shear stress, we need to calculate the weight. You know what I mean? And once we know these two values, then we will get the velocity. So that means at first we need to calculate the weight, okay, of the cylinder, and when we know the weight of the cylinder, then we will get the surface shear stress. And once we know the shear stress, then we will substitute the value here and we will get the velocity. Right. So the weight of the steel cylinder is rho g and the volume. This is the volume. You see the density is 8,000, gravity is 9.8. I believe now you can solve this problem. So if I solve this question this way, that okay, we will calculate the weight, then you can ask me why you are calculating the weight. So you see here, we need the velocity. Velocity is a function of shear stress, and to get the shear stress we need weight. So that's why we are calculating the weight at first. We will substitute every value. Now I got a question for you. For the diameter d, which one we should use? Is it 149.8 or this 150? Definitely this is 149.8 because we are calculating the weight of this cylinder, not the frame. So we just convert this millimeter into meter, and this is actually the length L. It is 200 millimeter, so now it's 0.2. See, we got the weight. Once we get the weight, then we will calculate the shear stress. It is equal weight over area. So the area of the cylinder, this is simple, pi dl. Substitute all value. This is the same 0.1498 and the L is 2. So we got the shear stress. Now this is the tricky part. Once we know this shear stress, once we know the weight, we will substitute the value, shear stress value here. So I actually want to tell you this dV or dr, it is the differential value, or you can say it is delta V delta R. So when we actually want to express some difference, change, so relative change, then we use this notation delta V delta R. So delta V is the variation of the velocity and delta R is the the rate, the diameter. So in this case, this is actually the cylinder. Okay, it is the moving cylinder, so it has velocity. On the other side, this prime, it is not moving, it is constant. So what we will do is, this is the velocity of this cylinder minus the velocity of the wall. So it will be actually 0. The wall velocity, it will be 0. And the diameter difference is, it is, you say this is 150, it is 149.8. So we just convert it into meter. And we substitute the value of the shear stress here, 2936, and all other values. This is the viscosity given in the question. You see, this is the viscosity given. So we substitute the value of viscosity. This is our ultimate target. This value is 0 and everything here. So you see, now if we simplify this, then we'll get this velocity. So that's actually the solution. So what we did here is, we initially calculated the weight, then we calculated the shear stress, and once we had the shear stress, then we substitute here and we got the solution. So that's it.